Hi, got a very interesting teardown for you today. Let's check it out. This one's actually a very old mailbag item. Thank you very much, Manu, for sending this in a long time ago in a mailbag galaxy far, far away. And sorry I haven't gotten around to doing this. Now, a lot of people are familiar with a product that looks something like this. You might think that this is actually an implantable pacemaker, but it's actually not quite that. It is different. It's a NeuroStimulator designed to send impulses into the nervous system. Yes, it is an implantable device, and it's designed to treat neuropathic pain, and like presumably very chronic, because getting one of these installed, implanted into you, is not a trivial thing. So yeah, you'd want to have like a real chronic case of neuropathic pain to actually go to this effort, because the first step is drugs and other opiates and other things to treat the pain. And yes, this one here is actually an implanted device, and yes, it's okay, it has been properly sterilized and everything else. So this used to be inside somebody's body. Sorry, I don't have the details. If you know the serial number, play along at home. Is that your one? Now, neurostimulators actually come in all sorts of forms, of which the pacemaker is effectively one of them. But this one doesn't go to the heart. This one, I believe, actually connects into the nerves going into the into the neck. But you can get ones that connect to your spinal cord and other locations. Now, this one's actually installed in the subcutaneous pocket, and I'll include a little photo of where that one's actually installed, and then the little cable, which we don't have sadly, which actually interfaces to these two connections in here. But there's actually multiple connections on here. You can actually see it's actually 4 pins, so each one of those contains 2 connections, and the cable just goes off to the implantable device. And yes, this is a non-rechargeable thing. It's got a built-in lithium battery, which basically effectively lasts the shelf life. I don't think they actually give a guaranteed battery life for this thing, but it's like, it's like 10 years in the plus, in the order of the internal battery in there, which we'll take a look at when we do the teardown of this thing. Because obviously you don't need much current at all, effectively nothing, to stimulate the neurons. So this thing could be running practically all the time, and it's not going to flatten the battery. Basically shelf life. So yeah, incredibly low power device. Now this is the Itrel 3 from a company called Medtronics, and they're pretty much one of the leading providers of these pacemakers, neurostimulators, and other things. So this one, I believe this design dates from 93 or thereabouts. I don't know when this particular one was manufactured, but they would, a lot of design effort and certification goes into these things. So once they design them, they typically sell them for a long, long time. Now, of course, these things use medical grade material because they are implantable or fully certified and tested, of course. It's got a titanium case. It's got a polyurethane interface connector block up here, and silicone rubber seals and other things. And they're actually, yes, they are little hex screws. Basically, you can get like a specialized tool, which actually, well, comes with it, I believe, when you buy it. Comes straight out of the box with the tool to actually get in there and adjust, well, tighten up the connector once you've plugged it in there. They don't just shove it in there and just rely on friction. They do actually tighten it up. And they're very thoughtfully provided the pinout on there. There you go for the 4 connections there. Because you don't want the doctor to get it backwards. That would really ruin your day. You come out of surgery doing cartwheels and believing that solar roadways and U-beam are good practical ideas. So I won't pretend to know the physiology behind all these things. Let's get to what everyone here's for. Let's tear this puppy apart. I think it's going to need the Dremel for this one. Ultrasonically welded titanium case, of course. And yeah, that looks serious business. And bingo, we're in like Flynn. Check it out. Actually, I went through like 1.5 of those Dremel cutting wheels getting through that titanium, but we're in, and you can see we've basically got that most of the space is taken up with the battery here. Now this is a lithium thionyl chloride battery, very common in industrial and medical applications like this. They're typically, you won't find them too frequently in any sort of commercial market or things like that. Now these are actually quite chemically reactive and can be exothermic, so they can actually, you know, heat up and potentially explode, but I'm sure that these are specifically designed internal, you know, very tight manufacturing tolerances to prevent all that stuff from happening. So I'm sure they've done their homework. And I'm using the Tegano microscope here to take a look. Now this could actually be a some sort of vent, or that actually might be where they filled the electrolyte perhaps, and then sealed it off, because it is a wet electrolyte, and it would actually react with stuff if it actually leaked out, of course. But look, they've actually using the outside of the case is presumably the negative terminal there. They've actually welded this gold like big stud thing on there, so that and then they can bond wire over there. So they've actually soldered, welded, or whatever that down to the can, and then they've got the wires buggering off in here through. Looks like a little. That feels pretty solid. I thought that was like some sort of plastic tube. It could actually be a glass tube or something, maybe. Not entirely sure, but anyway, it's designed to be an insulating tube going through there, taking the wire off, of course, so that it doesn't, there's no chance of it shorting out to the can here and shorting out the battery. But interestingly, you'll notice that we've got the double bond wires going over here like this. This is for redundancy, of course. In a critical implanted device like this, there's no way you're going to rely on one bond wire. Although they, having said that, over here that goes to the connections, they have actually just done the one bond wire going off to the case. So like if that broke, maybe it's not a huge deal. I'm not sure why they decided to do one there, but all the other ones you can see through the penetrators here, which go outside the case, they'd be sealed. Is that is a silicone? Yeah, that's rubber. That's rubber. I'm not sure if you can see that deform there, but that would be a silicone rubber seal around those penetrators there, which go outside the case. That's the term for anything that goes through a sealed case like this, is a penetrator. And we'll actually go out and just have a quick squeeze under there. Then you can see the wires actually coming out there like that, and then going into the little hex screws are in there. Is that something? Yeah, that's sort of, is that a I don't think, is that a re-enterable gel or something? Anyway, there's little, I believe there's little hex screws in there which then screw down to the connectors inside there. But yes, by the way, I have actually measured this battery and it measures 0. There's nothing coming out of it. So this one is completely and utterly dead. I'm not sure if 98 is the year of manufacture. That doesn't look like your traditional date code type stuff happening there, so I'm not sure what the deal is there. Now, of course, the interesting stuff is the PCB, and one of the first things I noticed, of course, were tantalum caps, and a lot of people might be surprised to find tantalum caps in there because they're notorious for, you know, catching on fire and stuff like that. But these aren't just some one hung low things that they're getting from the Shenzhen market. These would be fully qualified parts. In fact, every part in this would most likely by law, I guess, by certification, actually required to be signed off by the manufacturer. The manufacturers of these parts are not, in the data sheets, is very common to read, not not suitable for implantable devices. If you want to implant them or using life-saving devices, things like that, then you have to get specific permission from the manufacturer. So these would be very carefully selected, sought, ordered and certified and stuff like that. And we're not talking about using these for really like high peak currents and stuff like that. So it's not really a big deal. Anyway, we've got a ceramic substrate down here, and you can see that we've actually got, technically, a ceramic hybrid. Because that, if that focus, come on, you can see down in there, that is a hybrid resistor with a little laser trim mark. You'll notice there's another one there as well. So we've got two resistors. There could very well be components on the top, because I don't see any chips on here, so most likely on the bottom. But then we've got our multi-layer ceramic caps. We've got different types here. They'd all of course be specifically engineered, specifically chosen for the task. We've got one presumably some sort of tranny in there. What's a 133? I'm not sure. Those who those SMD code aficionados can go look that one up. And that is a 500 microhenry inductor. It's a bit hard to read that, but yeah, that's 500 mic. And what is that puppy? Is that another inductor? XE289 looks a bit different. So I'm not sure. That almost looks like maybe that could be the coil for the receiver, perhaps, because they've got to have a receiver in this thing to communicate with it, well, at least receive instructions from the handheld patient unit, who can actually, you know, play around with the settings and whatnot for this thing. Now, as for this puppy, got a ceramic top on it. It's only 2 pins, so maybe is it a crystal? Perhaps? I don't know. Weird. But of course, one of the most interesting things in here, look, it's a reed switch. There our contacts there, look, they're welded onto there. It doesn't look like they're soldered. It looks like they're welded down somehow, and they're actually blobbed in place like this. That's nice attention to detail, of course, and probably a requirement of the production process, that you actually blob them down first like that, let it set, and then you come along and go, you know, weld like that as part of the production process. But of course, the reed switch, that's a magnetic reed switch, and that looks like a normally closed one, actually. That looks normally closed to me if you look at those contacts. So you can switch either the entire device, or more likely just like the output or something like that, on or off via a magnet, which you place presumably on the back of your neck near where the unit is implanted, and that activates your reed switch. And you might notice this rubber here, that just sits in that little pocket. I really don't know what that's for. It's some sort of space filler or something. I don't know why they bothered. Bueller? So what we'll do now is just try and lever this puppy out. It's going to be stuck in there, and see if we can get the board out, because I think this battery has got to come out first. Yeah, that's held down with adhesive, and that is actually silicone adhesive, because it's got to be that's the only thing allowed inside these things. Well, actually on the outside, because I guess this is on the ultrasonically welded inside, but yeah, we've just got an adhesive strip there, so we'll just rip that off. Sorry for you bond wire aficionados, I broke it. Whoops. But yeah, that battery certainly is dead. There's no other identifying marks on that either. So you can see how there's some sort of plastic carrier in there. So we'll try and get a knife in there, and I'm going to have to break these beautiful bond wires. Bit of a shame, but we're going to have to sacrifice this puppy in the name of engineering education, I'm afraid. Oh, I've already ruined it. It was a thing of beauty. It was a joy forever. Getting the knife down in there wasn't too... Oh, come on. Geez, this is really tough. I've tried to get the knife down in there, but wouldn't have a bar of it. Completely stuck down, probably. All right, I'm pretty darn sure I'm going to have to apply greater force on this to get it out. I expect the ceramic hybrid base to crack before I get this out. Sorry for those who think this is beautiful and I shouldn't be destroying it, but oh, there we go. Yep, chipped it. And you can see the bloody glue under there. Oh, unbelievable. Somebody went ballistic on the production line. Why? But I think you can see what's going to be on the bottom. In fact, I don't think there's any other components apart from that one big blobbed ASIC in there, and trust me, they are running ASICs inside this thing. It's not gonna, you're not gonna find any sort of general purpose micro controller inside one of these puppies. They're going to be fully custom ASIC designed for ultra low power, designed for the exact requirements of what this thing needs to do. So yeah, it's just completely blobbed. I don't think there's anything interesting under there at all. Those numbers, just some sort of production code. But yeah, I don't think there's much else in there. Don't think I showed you that before, the beautiful gold-plated end caps on those tantalum capacitors. Wonder how much they paid for those puppies. Yep, I'm pretty sure that's the only thing under there is a gigantic chip. I don't know what size die that would be under there, but whether or not it's only a tiny die and they're just bond wiring stuff out and they just put in a huge encapsulant over the whole thing. I mean, you wouldn't need a huge, this is not, you know, you're not going to use like a 15mm die or something in there, but you know, things like the cochlear implants and stuff like that have massive requirements. I should have actually done this before I tried to attack that board in there. I thought I'd power it up, and sure enough, 3.7 volts, soldered some wires on there. Sure enough, 22 odd microamps. So yeah, that's exactly what you'd expect. This is a 2.7 amp hour battery, so you know, it's basically going to last the shelf life. So this is the basic operation of it. Now, little tip, you can get the magnetic hanger from your multimeter, and you can use that, hopefully. Does that change? Something's changing. And it's certainly starting to climb up. So maybe we've switched it on, we've done something. So look, I have no idea if I've damaged this physically. Those ceramic hybrids are pretty robust. They basically don't flex, they just shatter. So I don't think that I've actually damaged that hybrid. So looks like it might still be operational, but it's sort of steadily, the average current's increasing, 23 microamps. Slowly going up, I think. Let's actually take a quick probe of the waveforms here. I've got it on the battery comment, so, you know, I have no idea where the actual reference is. Let's start with the top one there. Aha, this is all 50 hertz stuff, so too much of a coinky-dink. Yeah, I can't see anything else. That's the mains frequency, so what's going on there? I don't know. I don't even know the amplitude levels for, you know, nerve stimulation, neurostimulation techniques. So, and yes, I've tried that with the magnet as well, and there's pretty much nothing doing there. So, sorry. Tell you what, though, we are getting something on one side of what I thought was that white ceramic package there, which I kind of guessed was a crystal. It's not. It's doing something else. So that's a slow time base. That's 200 milliseconds per division. 1, 2, 3, 4. Like, it's just over 800 and, you know, 810 milliseconds or something between those pulses. So, like, is that the stimulation period or whatnot? No idea. And I can actually get the magnet to activate the read switch. There we go. Let's try it again. Boom. There we go. Got it. So unfortunately, it looks like that's pretty much all we can do for this thing. And, well, there's not much in here at all. The teardown wasn't as interesting as I thought it might be, but I didn't know what I was expecting, really. I mean, it's not like it's a, you know, like a cardiac pacemaker or anything like that. It's just a neurostimulator, very low power neurostimulator that's designed to be implanted into the nervous system, the spinal column, or the nerves going into the neck, or even direct brain. I don't think this model does the direct brain stuff, but yeah, designed for neurostimulation for pain relief and, chronic, pain relief if you're desperate enough to get one of these installed. If you've got one of these, let us know. Leave it in the comments down below how it's working for you, what the procedure was to install it, how it was, do they have to calibrate the thing for your individual requirements? How often do you have to use it? Is it always firing, or do you only put the magnet thing on the back of you to activate it when you get in chronic pain or whatnot? Let us know, because I really don't know I don't know anyone who actually uses one of these things, but I'm led to believe they're, not that uncommon in the general population, because there's like I think it's 5 to 10% of the population or something suffers from some sort of neurological type pain. So I guess there's, got to be, at least a partial percent of people that are chronic enough to warrant one of these neurostimulators. So I hope you found that teardown interesting, at least. I mean, the most interesting part of this is basically, well, a lot of people say the boring part, and it is, but it's critical, is the certification of the design process. It can take years and years and years, and I've actually done some work for an implantable device company, and they, just the amount of effort that goes into, like, not only designing the ASIC chip, but designing every single part, qualifying every single part that goes into it, and everything else is just a ridiculous amount of work. From conceiving the latest product or, next generation product to when it actually gets released to market can be, like 5 to 8 years or something like that. It is a long development cycle because, implantable devices have to be ridiculously certified, so they certainly weren't trying to make this thing as small as possible. I mean, the new generations are probably thinner and smaller, but they've made no real effort to shrink that down, apart from the ASIC, of course, which probably does a fair bit, but it's probably a fairly complex ASIC. But yeah, I mean, this is basically just some large scale parts on here. Made no effort to get it down, especially with the connector and everything like that. So these would be pretty bulky inside you, but like I said, this is early 90s tech, I believe. It would have that's when the data sheet, the manual for this thing, so this probably would have been designed in the late 80s. So just take that into account. So thank you very much, Manu, for sending that in. And I did actually get another one, which is the Prime Advanced here. I actually got 2 of these, so I was able to tear down that one. But maybe now, and maybe in a separate video, I can tear down this. But it's probably very similar. This one is actually spinal cord neurostimulation. So it's actually a 16-channel job. So yeah, really much more advanced than this little, I don't know whether it's like 4-channel or whether or not it's like 2-channel or whatever with the Pros, but yeah, 16-channel job, probably extremely similar inside those. And this one is the non-MRI one. You can actually get, the latest version is like MRI compatible, so you can put them inside MRI machines and you're not going to, they're not going to explode or, sort of be extracted from your body or whatnot. So yeah, specific ones designed to be MRI compatible. Anyway, hope you enjoyed that look at implantable medical electronics. If you did, please give it a big thumbs up. And as always, discuss down below, especially if you've got one of these. Be really interested to hear from people who've got one of these puppies installed. Catch you next time.